Picture this, a single glowing atom, just floating in the dark expanse of space. Its electron cloud is constantly shifting, changing shape to this almost mysterious, silent rhythm. Well, what you're picturing in your mind right now, that is the very foundation of our entire universe. Welcome to The Explainer. Today, we're diving deep into the hidden language of the quantum world, quantum states.
So, what if you could know absolutely everything about a particle? And I don't just mean knowing where it is right now, I mean knowing every single possible thing it could do, even before it actually does it. Crazy, right? Well, in quantum physics, there's a specific concept that holds all of this incredible, mind-bending information at once. And without this hidden layer of data, we literally wouldn't have atoms, chemistry, lasers, quantum computers. Honestly, we probably wouldn't even have life itself.
Part 1. The Quantum Instruction Manual.
Okay, let's contrast the everyday world we live in with the bizarre microscopic world. In our normal, everyday life, describing an object is super easy. Take a football. You can point to its exact position, measure its speed, and know its exact direction. Once you have those numbers, boom, you know its definite state. But a quantum object, like an electron? Yeah, it doesn't work like that at all. It relies on a really strange set of probabilities and possible outcomes rather than just having one definite location or speed.
So a quantum state doesn't give us one exact, guaranteed outcome. Instead, it acts more like the particle's complete instruction manual. It contains absolutely all the information that can be known about that quantum system. It details everything the system might do and the exact probabilities of each and every one of those possible actions.
Part 2. Reading the wave function.
Now, how do physicists actually read this manual? Well, in quantum mechanics, a quantum state is mathematically represented by something called the wave function, which is written as the Greek letter psi. This wave function contains absolutely everything knowable about a given system. And you've probably heard of the famous Schrödinger equation, right? Well, when physicists use that equation, what they're actually doing is calculating exactly how this quantum state, this wave function, evolves over time.
Here's the catch, though. The wave function itself is kind of like an invisible blueprint. You can't observe it directly. But if we square the absolute value of psi, we get the actual probability distribution. Doing that math gives us the exact probabilities that we can physically measure in an experiment to find out where a particle is, most likely to actually be.
Part 3. Superposition and measurement.
This is where things get truly mind-bending. Think of a quantum state like a musical chord. When you play a chord on a piano, it's not just one note, right? It's several different notes ringing out together to create this complex, beautiful sound. Well, it's the exact same for a quantum particle. An electron's spin doesn't have to be strictly up or strictly down. Because of a property called quantum superposition, before it's measured, that electron can actually be a combination of multiple possibilities all at once.
So what actually happens when we force it to choose? When we measure it? Well, it happens in 3 steps. First, the particle is in superposition, meaning multiple possibilities exist at once. Second, we make a measurement, an observation occurs. And third, we get a definite single result. The wave function literally collapses from all of those complex possibilities down into one single observable reality.
Part 4. Powering modern technology.
Now, why does all this abstract math matter to you and me? Well, every single item on this list relies deeply on quantum states. We're talking about atomic orbitals, the chemical bonding that literally creates the molecules in your own body, the laser light used in everything from barcode scanners to global fiber optics, superconductors, quantum computers, and yes, even the MRI machines at your local hospital. Modern technology as we know it simply would not exist without us harnessing these invisible quantum states.
Part 5. Qubits and the future.
Let's look at the cutting edge. Compare how your current computer thinks with how a quantum computer thinks. A classical bit in the laptop or phone you're using right now is strictly a 0 or a 1. It's totally definitive. But a quantum bit, or a qubit, that is literally a quantum state itself. Because of superposition, a single qubit can represent a combination of both a 0 and a 1 at the exact same time, right up until the very moment someone measures it.
And this unique ability to hold a superposition is exactly what gives quantum computers their unprecedented, world-changing power. Because of this, they're able to process certain incredibly complex problems just so much more efficiently than any classical supercomputer ever could.
Part 6. Conclusion.
So the grand takeaway for today is this. Down at the absolute smallest scales, nature is not built on certainty. It is built entirely on possibilities. Every single quantum particle carries this complete mathematical description of what it could become. And from those invisible states, absolutely everything we see in the universe emerges. So it really makes you wonder, next time you look around, what invisible quantum states are shaping your reality? Thank you so much for exploring the quantum realm with me today in this explainer. Keep looking for those hidden structures in our world, and I'll catch you in the next one.